Let's talk about color. It's everywhere, right? It feels so simple, so fundamental to how we see the world. But what if I told you that it's all a trick? Today, we're going to dive into the physics of light to find out where color really comes from. And to do that, we have to start with a slightly unsettling but totally fascinating truth. I mean, just let that sink in for a second. That bright red car, the green grass, the blue of your screen, none of those things are actually those colors. The color isn't in the object. It's an illusion, a beautiful performance that light puts on just for you.
So that's the big mission for today. If a red apple isn't actually red, then what's going on? To figure this out, we need to hop in a time machine and travel all the way back to a dark room in the year 1666. And in that room is our guide, the one, the only, Sir Isaac Newton. Now, before him, people had all sorts of ideas about color, mostly that it was some kind of mix of light and dark. But Newton, with a really simple setup, was about to blow all of those old ideas right out of the water.
So picture this. He blacks out his room completely, except for one tiny little hole to let a single beam of sunlight in. Then he puts a glass prism right in that beam's path, and bam! On the other side, that single beam of what looked like plain white light just exploded into a full-blown rainbow. This was huge. Newton had just proved that white light isn't a color at all. It's actually every color, all mixed together.
And here's the secret sauce. Each of those colors you see in the rainbow is just light traveling in a different kind of way, a different wavelength. Think of it like this. White light is every radio station playing at once, and the prism is the tuner that separates them all out so you can see each one individually. And these waves are really different from each other. At one end of the spectrum, you've got red light, with these long, lazy waves, around 700 nanometers. Then, all the way at the other end, you have violet light, with these short, punchy, high-energy waves at about 400 nanometers. This one little difference, the length of the wave, is the key to pretty much everything we're going to talk about.
Okay, so we've got our new tool, wavelength. Let's use it to solve our first great mystery. Why is the sky blue during the day, but then it turns into this fiery red at sunset? Well, it's all about how these different light waves play pinball with our atmosphere. Now, there's a fancy name for this, Rayleigh scattering, but don't worry about the name. The idea is actually super simple. Our atmosphere is just full of teeny tiny particles, way smaller than a light wave, and when light hits them, it gets scattered all over the place. Okay, here's the play-by-play. Sunlight comes screaming into our atmosphere. It immediately starts crashing into billions of tiny gas molecules. Now, and this is the key part, those molecules are just the right size to be a real problem for the short wavelengths, like blue and violet. They get bounced and scattered in every direction imaginable. But the long wavelengths, the reds and oranges, they just cruise right on by. So when you look up, what you're seeing is a sky just filled with all that scattered blue light.
Okay, but hold on a second. If you're really paying attention, you should be asking this question. Violet has an even shorter wavelength than blue, so shouldn't it scatter even more? Shouldn't the sky be, purple? It's a great question.
And the answer is basically a 1-2 punch. First, the sun just doesn't send out as much violet light to begin with. And second, for the violet light that does make it here, our eyes are just way more sensitive to blue. So you put those two things together and yep, blue wins the contest for the sky, hands down. And get this exact same science explains sunsets. When the sun is way down on the horizon, its light has to travel through a much thicker slice of atmosphere to get to you. By the time that light reaches your eyes, almost all of the blue light has been scattered away, leaving only those long, tough waves of red and orange to make it through. It's the same physics, just a different angle. All right, so scattering? Check. We've got the sky figured out, but what about those crazy, swirling, psychedelic colors you see on a soap bubble or in an oil slick? That's not scattering. This is something else entirely. We need to introduce a new character to our story: interference. So this happens when light hits something incredibly thin, like the wall of a soap bubble. Some of the light bounces right off the front surface, but some of it actually goes through the film and bounces off the back surface. So now you have two separate light waves coming back at your eye, and how they meet up is everything. If those two returning waves are perfectly in sync, if their peaks and valleys line up, they join forces and amplify each other. Boom! You see that color and it's super bright. But if they're out of sync, they completely cancel each other out. Poof! That color just vanishes. And since the bubble's wall is always changing thickness, the colors that get amplified and the colors that get canceled are constantly shifting. That's your swirling rainbow.
Okay, so you thought soap bubbles were cool? Let's take this whole idea of interference and turn it up to 11. We're going to go from a fragile soap bubble to one of the most brilliant and permanent displays in all of nature, the peacock feather. I mean, seriously, look at that. How is a color like that even possible? It almost doesn't look real. For centuries, people just assumed it must be some kind of incredibly special blue pigment, right? Well, the truth is way, way cooler than that. Get ready for this, because it's a big one. There is absolutely zero blue or green pigment in a peacock's feather. None. The feathers are actually made of keratin, which is brown. It's the same stuff as your hair and fingernails. The color you're seeing isn't a chemical. It's an illusion created by physics.
This amazing phenomenon is called structural coloration, and it means exactly what it sounds like. It's color that's created by the physical structure of something, by its shape on a microscopic level, not by the chemical it's made of. So if you could zoom way, way in on a single little piece of a peacock feather, you'd see these incredible microscopic tree-like structures. These are called photonic crystals, and they act like a super advanced version of the soap bubble, precisely designed to bounce light around and cause massive interference, amplifying the exact shades of blue and green we see and canceling out all the others.
And let's be really clear about this difference, because it's profound. A blue flower has a pigment. That pigment absorbs all the other colors and reflects blue back at you. But a peacock feather cancels all the other colors through interference and only lets the blue way to survive. One is chemistry, the other is pure physics, pure geometry. And that's why the color shimmers and changes when you move it. You're literally changing the angles and the paths the light is taking through that structure.
So from a simple prism in a dark room to the entire blue sky to the impossible geometry of a peacock's feather, we see this incredible pattern. Color isn't some static property of the world. It's a dynamic story that light is constantly telling us. And I think this is the most amazing takeaway from all of this. When you look at the world now, you realize you're not just seeing colors. You're watching physics happen live. A beautiful sunset isn't just a pretty picture, it's a massive demonstration of Rayleigh scattering. That shimmering bubble isn't just a toy, it's a canvas for thin film interference. You are watching the fundamental laws of the universe paint reality right in front of your eyes. So my challenge to you is this. The next time you go outside, look around a little differently. Look for the physics hiding behind the beauty. Look for the structure behind the color. It's everywhere once you know what to look for. What hidden physics will you see next? Thanks for joining me.